We're now ready to get into the other part of today, which is sort of an introduction to the course. Why are we here, and what is it we hope to learn? So we start with the question, what's the differential equation? Now, the word differential is not a common word. We don't oftentimes think about it, but really it's a substitute for the word derivative. So if you think about it, one thing you could say is like, oh, it's a differential equation. It's some equation involving a derivative, which is perfectly fine. But what's a derivative? A derivative just means something's changing. If you like, think about the word differential. It looks like the word difference. So there's change involved. So really when we talk about a differential equation, it's an equation which involves some quantity which is changing. Great, wonderful. Well, that's not so scary at all. Now, what are things that can change? Well, a lot can change. And there's a lot of examples out there, but we're just going to highlight three, because these examples we're going to see over and over again throughout the semester as examples. Growth and decay. Now, you might say, why do we care about things like that? Well, maybe you're a biologist. You say, I want to know how a population is growing. Well, that's a good differential equation. You can use that to model that. Maybe you're working in atomic physics. I want to know what's happening to my radioactive substances. Well, that comes down to another differential equation related to decay. In fact, it's basically the same types of models involved. And then another thing, mixing. You have things mixing together. Why might you care about that? Well, maybe you're in chemical engineering. You're mixing some substances together, and you want to make sure you know what's happening. You want to control a reaction. Well, we can help. Differential equations can figure that out. Then you have oscillating or vibrating. Things wiggling, moving up and down. Why might you care? Well, maybe you're a mechanical engineer. You're designing some shock absorbers for your vehicle. You want to say, look, I really want to make the shock absorbers just right. Not too bouncy, but, not too stiff. So you can use differential equations to model. Or maybe you're an aerospace engineer. So I've got a plane. I want to make sure I understand how the vibrations will affect the wings and whether or not they'll fly off, because I hear that's a bad thing. So a lot of things can be modeled using differential equations. So it's actually an incredibly rich field. So that's what we're here. All right. So you might say, well, you've talked about differential equations. Why do we care about thinking about it in terms of the differential part? Why not just look at the original function? And here's where it gets an important point. Sometimes it's easier to understand or relate to how things are changing than it is to figure out what it actually is. So that's why we care about differential equations. It can help us describe things relatively simply, but we can have very complex situations. So what is it we hope to achieve then? Well, we hope to understand a few things. We want to know, how can you set up a differential equation? In other words, there's a very fancy word which we'll be using over the next week or two. There's the word called modeling, which says, I have this scenario. How do I model it? How do I get things related to one another? Now, the big thing here, this is the ideal, is to find an explicit formula for what the quantity is doing. And to be honest with you, this is where we're going to spend most of our time, is this part right here. And you might leave this class thinking, man, these mathematicians, they've got differential equations figured out. Well, I spent a whole semester solving them. But I'll tell you the truth. We don't have them figured out. We're going to see lots of special, really easy cases. Now, you might say, it doesn't feel easy, but trust me, it gets worse. So we're seeing the easy ones. And so, yeah, we know how to solve the easy ones, but 99% of differential equations we can't solve this way. So, well, what do you do in that case? Well, that's where the other points come in. Maybe you can say, look, I can't gain an explicit solution, but I can understand some behavior. Like, if I were to let things go and time runs for a very long time, what's going to happen? Maybe I'm modeling some population. Is my population going to explode? Is it going to disappear? Is it going to reach some other state? We can figure that out even if we can't find an explicit solution. Or we can learn to find approximations. So there's sort of two concepts of approximation. One is numerical approximation, which is probably, in the world of engineering, that's how most approximation gets done. And you'll learn that very likely at some other point. Another way we can do approximation is to say, well, we put on our old Calc 2 hats. You might remember Calc 2. I know, it's coming, it's good stuff. Now at the end of Calc 2, do you remember what the topic was? Series. Now what's, oh, I see like people are like, oh, yeah, I know. So series, the idea of series is every function's a polynomial. And so you can approximate every function by a polynomial. So we're going to actually end our class also with the same setting. We're going to come back the last week of material, talk about how we can use polynomials, which is really just a part of series, to find good approximation to our quantity. All right. So we don't have very many tools, but I want to do an example that sort of highlights what's going on here. And we'll start with something fairly simple, fairly straightforward. A simple question. How does a spring move? So you can imagine we have a spring. So I have here a good approximation. It's a slinky. And you can let it go, and you can see it moves. Like, ooh, ah. Now, you could also get some movement by just sort of holding and moving forward. And what you'll see is it's moving up and down. Now, the question is, what's the bottom of that spring doing? So if I were walking and I were just following the bottom of that spring, what would I see? A wave. Okay, somebody has suggested a wave. What does it look like? Well, let me show you some candidates here. Maybe it looks like this. Now, people are probably very skeptical about that one. Is that what the spring looks like? No? Well, I said very skeptical, so you're probably like, that must be a no. All right. Well, maybe it's doing something more like this. All right, maybe that goes up and down. Or maybe it's doing something else. Maybe it's doing some kind of weird thing. All of these are saying, I'm going up and down. But none of these feel right. Does anybody have like a good guess? Like, I think it's this. A sine curve? It could be like sinusoidal, which is a fancy way of saying it looks like a sine curve. All right. So maybe it's a sine curve, but are we sure? Is it? Or have they been lying to us? Is it some sort of like secret that the springs are hiding from us? Maybe it is. Maybe it isn't. Okay, so we're going to figure that answer out in the next, 10 minutes, give or take. All right, so we're going to start with something called Hooke's law. All right, so a brave soul who's taken physics before. Can you tell us what Hooke's law says? Anyone? Has anyone taken physics before? Okay, some people have said yes. Okay, there's a brave soul.
Force of the spring is equal to the coefficient of the spring multiplied by the stretch of the spring.
Okay, force of the spring is equal to the coefficient of the spring multiplied by the stretch of the spring. Does that sound right? Maybe?
So it's a negative kx, so f equals negative kx.
All right. So, here's the basic concept. Suppose you have a spring and you stretch it. Now the question is, what does the spring want to do? It wants to go back, right? So a spring likes being in its natural state. And so if I stretch it, there's a pulling coming from the spring saying, no, go back, go the other way. Okay, so the question is, well, how much is it pulling? So that's where the force is coming from. There's a force pulling me back to the steady state. So the idea is the following. So we'll draw some pictures here instead of trying to do it with an actual spring. So if I have a spring, So here's my spring. This is its happy place. It likes to be here. And now, if I take that string and I've stretched it, then what happens, and you can imagine there's a little tiny weight here. Doesn't really matter. The spring is trying to pull it back. Now, the amount of pull that the spring has, that's the force, is equal to, all right, so here we have a spring constant, that's K. I'm leaving a suspicious gap here. And then there was like the offset. So the offset is how far down you move. So we'll call it X. X. Now, I have left a suspicious gap there. Somebody mentioned something. I don't know if people heard it. What goes in the gap and why? A negative sign goes in the gap, and why?
The force is acting in the opposite direction.
The force acts the opposite way. So if I'm in a place where the x is positive, it says, no, go back, because you want to go to 0. So if I'm x positive, it says force should be pulling you towards 0. If I'm x negative, it should be pulling you towards 0. So the force should be positive. So that's why there's a minus sign. Okay. Now, you're probably thinking, that does not look very much like a differential equation. But hold on. Where does force? Mass times acceleration. How do you find acceleration? Derivative of velocity. Okay. How do you find velocity? Derivative of position. Okay, so if acceleration is the derivative of velocity, velocity is the derivative of position, how do I get from position to acceleration? X double prime. Okay, so we've now gone to mx double prime is equal to minus k times x. All right. Or if you like, you can say, hey, the second derivative is this quantity minus k over m times x. This is a differential equation because it involves a derivative. A differential equation is an equation which involves a derivative. All right, so we found a differential equation. Great. Now, we want to solve it. Well, we don't have a lot of tools. That's okay. First off, let's make some simplifying assumptions. This is oftentimes what we do. Let's just assume this is 1. Eventually, we'll be able to do it when it's more general, but let's just start with this equals 1. There are cases where it does equal 1, so that's not so crazy. And now, the question. We're told x double prime is equal to minus x. So I'm thinking of a function. A function where I take two derivatives, I get negative of the function I started with. So we're not going to solve this by using any fancy tools. We're going to solve this by thinking like, have we seen something like this somewhere before? Have we seen something like this somewhere before? Sine x? Okay, so what's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. Oh, good. You remembered that. So we are like, ha ha, hoo, ha ha ha. So we have a solution. Now we already used x here, so I can't use x again. So I'm going to use t. And oftentimes you'll see that we like to use t here. We have it. One solution is sine of t. Is any other function that does that? Okay, does cosine work? Derivative of cosine? Negative sine. Derivative of negative sine? Negative cosine. So cosine also, now, wow, amazing. Two functions. I didn't give myself very much space here. Bad planning. All right. All right, so good. Are there any other functions that have this property? 0 has this property. In fact, 0 is a lovely thing. What would 0 correspond to in terms of our spring? If I had our solution as x is 0, what does it mean? we're in equilibrium, or we're in the resting position. It is a perfectly valid solution, because if you take the derivative of 0 twice, you're still at 0. Okay, so good. 0. Any others? I know I'm putting you a little bit on the spot, but that's okay. It's our first day. We're among friends here. We all like each other.
E to the negative x. Wouldn't that work?
Well, what happens when you take the derivative of e to the negative x?
Negative e to the negative x?
Negative e to the negative x. Now you take another derivative.
E to the negative x.
You get e to the negative x. So we're the function we started with, not the negative of the function we started with. But it is a good guess. In fact, we could modify it and do something really complex. But people are like, oh. Nobody wants to go there, so I guess we won't go there. All right. What about if I doubled sine? 2 sine t, would that work? Yeah, 3 sine t, 4 sine t. What if I added sine plus cosine? Yeah, that would also work. I mean, it's not like an instant, like, aha, it's true, aha. You know, later on in the semester, we'll be like, aha, yeah, you know, we'll see that. But we're not there yet. It turns out that you can multiply sine by anything, multiply cosine by anything, and add them together, and you're still going to work. And here's the amazing thing. That's it. Those are the only solutions. And now we can say definitively, yes, if I have a spring, at least in this simple case of 1, then I have to look like the sine curve, because springs behave like a sine curve. Now you might say, well, how did springs learn trigonometry? They haven't even gone to high school yet. Well, it's not that they learned trig and they didn't pick it as like, this is my favorite looking curve. It's we started with a simple differential equation and we followed the consequences. So we modeled it. That was this setting up Hooke's law. And then we solved it. And then we can understand properties. Now you might say, well, what if we don't have k over m equal 1? What if we have k over m equal something more complicated? What do you think would change about our answers? Well, would the coefficients change or would something else change? So coefficient was a suggestion, and maybe. So you're thinking something here will change. So vaguely, what would you think would happen to it? And when I say something here, this t on the inside. More stuff. Yes, that is the correct answer. So there's going to be more stuff. So when you have this part here, you think, well, okay, I have to take 2 derivatives, and I have to get a k over m to appear. When you're taking the derivative of the sine, well, if it's just normal sine of t, okay, it is what it is. What if I take the derivative of like sine of 2t, and I took that derivative twice? What would happen? You'd have like a 2 come out, and a 2 would come out again. So you get like 2 squared. So whatever I have multiplying by the t, every time you take a derivative, it comes out. So what I need to have is whatever multiplies by the t, when I do it twice, I need to end up with a k over m. Well, any idea what might do that? Yeah. So x of t equals a sine of square root k over m t plus b cosine square root k over m t. So that would be the most general solution. So every single spring behaves like that. And this is just our first day. Wow, this is amazing. Who knows what we'll be able to do by the end of the semester? Maybe 2 springs at the same time. Maybe. Now, of course, we're going to get more complicated. And you might say, well, could there be something interesting? Well, you could imagine they have x double prime plus 0.00001 x prime plus x equals 0. And you might compare it to x double prime minus 0.0001 x prime plus x equals 0. So if you think about this, another way you could have written this is x double prime plus x equals 0. So we could add just a little tiny bit, or maybe we could subtract. Now, you might say, could this really make a big difference, this extra term here? What do you think?
No. Yes.
Okay, we've heard a no, and we've heard a yes. Both are kind of correct. Short term, no. It's very small. Long term, yes. Long term, one of these springs is basically going to tire out and be like, ugh, and it's going to stop. The other one is going to get really excited and oscillate wildly until the system mechanically breaks down. Can you tell which one is which? By the end of the semester, you will. You'll have the tools. We'll get there. All right. So, quick, one more slide here to go through. So we have examples of differential equations. So again, a differential equation, it's an equation which involves one or more derivatives of a function. So you might have something like dx dt equals x cubed plus x times t. So you might see it in terms of this d something over d something. This involves the first derivative. We might look at higher order derivatives, in that we will look at higher order derivatives. D squared y dx squared minus 5 dy dx plus 6y equals 0, which we could have written as y double prime minus 5y prime plus 6y equals 0. These are the same differential equations, just written in different notation. So we want to be comfortable looking at these back and forth. You might also see something like 2xy dy plus y squared dx equals sine of x dx. You could be even more exotic. Y prime plus arctangent of y prime equals 1 over x squared plus 1. I like it in that it has arctangent. I don't like it in that it's hopeless to solve. But you know, so it's a love-hate relationship, so it's okay. Or you might have something like y prime equals e to the 2x plus 6 cosine 3x. Now you're probably looking at this and saying, is that really a differential equation? Is it? I mean, it's under the list. Is it a differential equation? Yes. Why? Because there's a derivative. If you see a derivative, it's a differential equation. They might say, but wait a second, this looks like Calc 1 stuff. You're right, it is. We can solve 2 differential equations today. Let's do it. What's y? So, what do we need to do? Integrate. Yeah, e to the 2x divided by 2, or 1/2 e to the 2x. And then, integral of cosine. Oh, you were so good with your derivatives. Negative, positive, positive, negative. There's lots of negatives, but now the positives seem to be taking over. Is that right? Oh. Yeah, that's right. That's right. Okay, what else? 2 sine 3x. And is that it? Plus c. Plus c. Now you might notice something. Here, there's a plus c on the end. You're like, yeah, whenever we integrate, there's always a plus c. And essentially, differential equations is going to involve a lot of integration. So be prepared to integrate. But wait a second. Where was our plus c over here? We solved the differential equation, and there was no plus c. Or was there? Well, it wasn't a plus c, but what do you notice about our solution? We have a and b. And you know, it must be like the alphabet telling us something. A, B, C, they must all be in on it together. So the point here is you have like this free constant, a free choice. And actually, there's something to note here. You take one derivative, you get one thing to pick. You get your c. Here, when we talked about the string, we had two derivatives, x double prime. So we should have two things to pick. And that's our a and our b. So now we're going to see constants showing up, but they don't always have to be at the end. In fact, they rarely will be. Wow, cool. All right, so how do you solve differential equations? I found this nice quote this summer. In order to solve a differential equation, you look at it till the solution occurs to you. Now, that's not the best way, but I will tell you, that's how a lot of math gets done. A lot of science gets done. You're like, how does this work? I don't know. I'll stare at it for a long time. Then you have like an idea. And then you write it. When you write and you tell other people about it, you're like, it was always obvious. Yeah, right. Give me a break. Come on. It wasn't obvious. So what we're going to do is build on the knowledge of our forebears who spent their time staring at it, and then they saw there were patterns. And we're going to build on those patterns and say, okay, look, here are some patterns, and here are ways to solve them. So this is where we're going. So in the first part of the course, starting this week, we're going to solve first-order differential equations. And there's a couple of different types. And you'll see that first order, and first order, by the way, means one derivative. So the order is how many derivatives you have. So first order, one derivative. And we'll see that there's a few nice cases, separable, linear, and exact. Then we'll go to higher order differential equations. So that means like second order, third order. And the further we go, the less that we can do. But we'll still see that there are some very nice cases and some very nice tools. So that'll be the first part of the course. And then comes our exam 1. All right, great. After that, we go into systems of differential equations. Now, what is that? Well, you might have many things changing all at the same time, all interacting together. Like, that sounds cool. That sounds like things that might actually happen. What's our main tool here? Well, our main tool, this is exciting stuff, matrices. Yes. I know. I also am excited. I feel the same excitement. I know. We're going to be there for a couple of weeks, and then we're going to have exam 2. So exam 2, it's all matrices all the time. So good stuff. Good stuff. Don't worry. If you haven't gone good at matrices, you will get slightly better. And then the last topics are Laplace transforms. Now, Laplace transform says, maybe we don't want to do differential equation problems. Maybe we want to do algebra problems. And what it does is it says, I'm going to turn your differential equation problem into an algebra problem, and then life will be good. So that's what Laplace transforms does. And then the thing mentioned earlier, we're going to use series. And series are a great way to do approximation. So that's where we're going with the course.